Okay, welcome everybody to this session of the Cloud Native Day about big data. And I'm going to tell you today how we at IBM do big data in the cloud in a very cloud native way, specifically how we have a form factor of data lakes in the cloud. Okay, welcome everybody to this session of the Cloud Native Day about big data. And we don't call it just a data lake, we call it a serverless data lake, because that's expressing really how we really consequently designed this in a very cloud native way, not just as a cloud native architecture, but also for cloud native solution building on top of this data lake platform. So I'm Thorsten Steinbach, I'm an architect of IBM Cloud, taking care specifically of our cloud data lake services. So a lot of the things that I'm going to show you is really stuff that me and my team are building ourselves every day here at IBM. How we got here is actually a brief context historically. So big data obviously is not a new term, right? And in big data systems and form factors exist for a while. Actually, there have been data warehouses around for quite some time already that are well established and deeply optimized and integrated to really serve this workload very well and very efficiently in a very performant way to do specific terabyte up to petabyte data analytic use cases. Nevertheless, Hadoop actually gained traction about 2 decades ago. For good reason, because it added a lot of openness and more capabilities of more types of workloads to the game. Openness in terms of data formats, data types, data sources that can be supported. Openness in terms of libraries and languages and that you can use to express your analytics, algorithms, queries, but also openness in terms of how you deploy it and what kind of hardware, and how you scale it also. But actually, that's not enough really if we want to go to the cloud and really leverage cloud benefits, right? What really the cloud economy of scale benefits promise. How can we do this for big data? We cannot just take Hadoop or enterprise data warehouse as is and deploy to cloud and expect this will just work out magically. We really need to account for the cloud native disaggregated architectures in order to achieve elasticity, a pay-per-use capability, and so on. This is a lot based, because we are talking about big data and data in general, about decoupling state, the data itself, from the compute. And that's why things like object storage are playing such an important role, because they do exactly allow us to do that. So that's what we're going to talk about, the cloud native revolution, if you like, for big data, which is driven by cloud and cloud as a service form factors. But before we go there, first a brief overview of how we define a data lake. The data lake and the cloud data lake for us is really something that can acquire data from either data that already is stored somewhere in your systems of record databases, and then this data needs to be copied, ETL'd into this data lake, typically in a batch fashion, or you can also do this in a replication streaming style fashion using CDC. CDC stands for Change Data Capture, where basically you capture and change feeds of the databases, and you're continuously applying this into your files, into your objects in the data lake. And another fundamental way of cloud data lakes, actually where cloud data lakes playing a much more role nowadays, is for data in motion directly, where data that is not actually acquired anywhere else, it just streams in or streams through, or basically it just appears, and if you don't do it, it's gone. Things like application logs, for instance, or user behavior, click streams, audit trails, audit events, IoT events, and things like that. That's immensely valuable data, and the cloud data lake is a perfect means to get a hold on this kind of data by streaming it into the data lake. Now, the data lake itself provides stages of basically working through this data, starting from exploration, if it's very new, unknown, fresh data, getting an understanding of the data, of the quality of the data, of the structure of the data, then preparing the data into a more defined schema, pattern, quality, enriching it with other metadata that you might have somewhere else, and optimizing it. Optimizing is very important because that means, especially in a data lake, already in Hadoop, this has been the case, but it's even more important in cloud data lakes. How you lay out the data on disk matters a lot for your analytic capabilities and performance. So optimization in terms of formatting, layouting, partitioning, also creating indexing on top of the data is a lot of things that you need to do. And then you can start to consume the data. For instance, in a simple batch query. That's basically a simple thing that was comported out of the box. When you get into more interactive use cases or higher qualities of service, like a transactional consistency that you need for your analytics and your queries, that's where often and typically you still see a lot of data warehouse. I'm talking about more really classical data warehouses playing a role. And then you have an ETL going on from a data lake, or it can also be in the cloud, from a cloud data lake into a data warehouse to drive those type of workloads specifically, right? But this is something, because the data lake itself, cloud lake is designed to be very elastic and scalable and so on. And the data warehouse basically is a much higher expensive and integrated thing. It's a different cost factor and also operational cost factor. That's why what you see nowadays, there's a lot of innovation going on in order to pull in qualities of service into the data lake itself from a data warehouse that traditional data warehouse can only do. And that's what this term that you might have heard about data lake house is expressing, exactly that. More guarantees for interactive query, transactional consistency of data. That's what data lake house basically means over just a plain data lake. Now, IBM has a fundamental stack that we are using to serve such an architecture of a cloud data lake, that it consists of serverless basic components, like a serverless storage option, that's our cloud object storage, a serverless runtime option, it can run any kind of code, and it can automate any kind of code execution in an event fashion, that's the cloud functions. And now also we have basically a complete new generation of that is even more capable. That's our IBM Cloud Code Engine. And we have serverless analytics, which is a service that you will see closer in the next few minutes. It's IBM SQL Query, which is the core service of this data lake itself, that allows you to run any kind of SQL operation in a serverless fashion. Each of those services itself is highly available and serverless and consumed by use, paid per use. Now, the core service that I already mentioned, that is basically for our Cloud Data Lake platform that I just shown you as part of this 3 serverless components, is this SQL Query service. And it actually serves 4 different pillars of capabilities. And that's important to understand because the service name doesn't reveal that. SQL Query, right? One is really, and that's what you might imagine what SQL Query is about, is analytics. I can do analytics, which means I can run queries on top of data in my data lake. And the data in the data lake primarily means object storage, but as you will learn, this can also now mean data in motion that is more for ephemeral status in Kafka. So I can run queries on this, obviously. That's SQL Query, what SQL Query promises to do. But what you can also do with that, actually at scale, and also in the same serverless fashion, is data transformation. You can ELT, as a term often is referred to, prepare the data in an ELT fashion on cloud object storage to do all this kind of preparation, enrichment, optimization, and so on, just using serverless SQL jobs. What we also do, and that's something new, that basically is rather new, that we're just rolling out now, is data ingestion. So how do you get the data into the data lake is also being done by the service, because it actually will, or it can pull from Kafka. So whatever basically you can stuff into Kafka, this is where you can take it in a serverless fashion into the data lake using this service. And the 4th pillar, which basically touches all 3 of these others, is data management. Data management is nothing else than a table catalog. So this is the metadata, the table metadata that you manage in a table meta store in this Cloud Data Lake service here. So that you can, when you have ingested data, prepare the data, you can create a table for this data, or maybe views on top of this data, and then you can use these to analyze it in your applications. So that's the basic idea and feature set that you find in this core service in IBM Cloud Data Lake platform. It's a brief architectural view, not very deep, but what's running behind the scenes is Apache Spark. And that's giving us a lot of capabilities to do this breadth of capabilities like ingestion, data preparation, query analytics. Metastore, the Hive Metastore is something that we are using here, that we are basically managing and making backups and keeping high available for the user out of the box. We have added a lot of IBM IP for instance, for data skipping. That's an indexing feature to accelerate queries, to process specific types of data, like time series data. We can treat really timestamp data as a special data type and do a lot of operations on top of that, or location data as well. But then that's basically it. The application does nothing else than submitting SQL jobs, SQL requests to the service, and the service figures out what to do with it. It reads data, processes it, it writes data out, and then basically data can be consumed by the application, whatever the application wants to do with the results. The usage of, or the basically interaction with this service is multifold, or with this platform, I should say, because it's really just a core service of an entire platform. You can just go, there's an interactive way to use the service through an SQL console. There's an interactive SQL console that you can use to run SQLs, to preview the results and things like that. But we have also embedded the service into other web UIs, user interfaces, like for instance in the cloud object storage context, when you're just browsing the objects in IBM Cloud, you can just see, oh, we recognize actually, oh, this is an object that is structured data. It's a JSON, or this is a Parquet file, or we can recognize that, and then we basically directly feature, oh, you can query this object, or it can be a folder also, and then you can query this folder with many partitions as a single data set, and launch a SQL from there. And in a similar way, we are integrating this SQL capability for the ingestion case that I mentioned before into the event streams console. Now, event streams, in case you don't know this yet, this is the IBM Cloud service name for our managed Kafka. So this is where you can go have Kafka instances with topics, and you can now go to the topic and say, you know what, this topic is something that I would like to run an ingestion job on. Whatever it comes in from here, just basically launch an ingestion job into Cloud Object Storage, and that will also drive the SQL query behind the scenes to do this streaming SQL job that reads from Kafka and writes to Cloud Object Storage into Parquet. So but that's more for building things, right? If you really want to interact and consume data on that object storage through this Cloud Data Lake platform, you can go, for instance, to Watson Studio and use notebooks. That's something that is supported out of the box, and to create data science projects and data science flows that run big data OLAP queries on your Cloud Object Storage from notebooks, and then work with the results, train a model whatsoever. What you also can do is, if you want to deploy SQL jobs, specifically if you have built, say, pipelines, right, of data transformations, you may want to automate these things, that they should run every hour or at a certain event trigger. You can use Cloud Functions. Cloud Functions are basically giving you the hook to automate this execution of this pipeline. And finally, for everything it's available, there's an SDK, right? There's an SDK for just SQLs itself, that's JDBC. We also, in the meantime, have through third-party ODBC support. So if you have ODBC, JDBC applications, you can connect against the data lake that way. You can also use our plain REST API, or you can use some more opinionated APIs for Python, for instance, which is a very rich SDK that provides you a lot of simplification and exposes very simple user interface or developer interface on top of your data and Cloud Object Storage with SQL capabilities, just using standard Python pandas data frames. So those are some examples of basically the different usage patterns and integration points that you can have for this platform. Now, I wanted to go now a step further and explain a little bit what's going on, not just at IBM, but it's actually something in industry trend that we see and how we respond to it in IBM. The way we are able to deliver this promise that I explained at the beginning, right? To say, you know what, we have data lakes and have data warehouses, but actually you want to have an integrated thing that has all of the elasticity, but it can do also data warehouse things. We call it a lake house. That's the way how we can get to it, by a very strict and clear and very conscious separation of processing and state. Now, processing itself is already a multi-layer thing, right? We have the basic runtime capability where we can run any arbitrary code. In IBM Cloud, that's the code engine. That's our serverless container service. On top of that, we are building our Spark service that basically runs Spark jobs on demand at any scale that you want, using the serverless containers. And on top of that, we are running the SQL service, the serverless SQL service, which just features the Spark SQL API in a special, easy, opinionated way. Each three of these layers you can use, right? You can use just the serverless SQL layer, or if you want to do something outside of SQL, you can go to the serverless Spark layer, or if you want to do anything outside of Spark with any other engine or runtime, you can go to the serverless container layer, right? But these things build up on each other. But these are all stateless compute layers, so to speak. They in itself can scale entirely independently of the data. That's the big thing here. And the data itself is layered. That's very important. Obviously, we have the payload data itself. Big data, terabytes, petabytes of data stored in object storage. Yes, in a certain format and layout that we consciously choose and also optimize, like partitioning, using Parquet and so on. But it's just data at the end. What, however, is the key to success here is a strong metadata layer. That's really important. We are actually investing a lot in making metadata a thing. So on one side, it's really the bread and butter table or data set structures. There's a Hive metastore that exposes or that manages, this is a set of tables, and this table has the following partitions, and these are the objects for this partition. Similar on the data in motion, there's a Kafka schema registry that defines the schema of the data in topics. On top of that, that's more bread and butter. On top of that, we are adding indexing, which is another form of metadata where we have scanned all of the data and recorded a lot of statistics about the data and use them to accelerate queries. The index itself is also stored in object storage, but just the mere existence of this indexing service and how basically it is linked to the data itself, that's the metadata. Then actually, and that's an industry trend, that's not something that IBM invented, but we are really heavily adopting that, is there are table formats, these so-called asset table formats that are coming up. So on top of plain file formats, and a file format is something like a CSV, right, or JSON, or can also be more complex like Parquet, ORC, or analytic table format or file formats. And on top of that, table formats are evolving, which is basically a compound format of files on disk, along with manifest files and libraries on top that can interpret and understand these. And what is achieved with these is really something like asset level transaction guarantees, right? You can write many different things in a complex long-running operation, but just the final update will be made to the manifest file, which will basically tell everybody, oh, now this is live. Now that basically it's committed, and now everybody can see these changes. And Delta Lake and Iceberg are the two front runners here of these formats that I want to call out here, that are industry standards, open standards. And finally, IBM has a stronghold in governance, and we definitely want to fold it in. So what's Knowledge Catalog product is our governance catalog service here, which tells us things about this data has basically a certain governance policy that should be protected, this file. Certain data must only be exposed mask to, or not at all, to certain users because it's personal information or other confidential information. That's what governance metadata is controlling. That metadata actually is what turning this whole disaggregated stack in combination then from a plain data lake really into something eventually that we call a lakehouse. Now let's look a little bit behind the scenes, a little bit more architecture here. Not entirely new, I already mentioned metadata. So metadata is the all-encompassing thing here. But we have at the center this SQL query service, which supports queries on data, and which is on one side data at rest, which is Cloud Object Storage, and on the other side data in motion, which is Kafka event streams. Then you can basically not just run queries there, you can also run transformations there. So stream transformation or transformation on disk. And then you can also connect those two. And that's actually the thing that we are rolling out right now, which is the stream data landing, that you can say, you know what, I run a job that continuously reads from here and writes to there. So that's the whole idea of the core platform, basically, that the philosophy here behind. And then you can connect other engines. For instance, on the input side, you can use CDC, Change Data Capture, and there are things like replication products of IBM, but there are also open source alternatives like Debezium that allow you to do log capturing on databases, basically, and produce change feeds. That could be an input, basically, to Kafka. And on the consuming side, because we're using open standards, open file formats like Parquet, but also these table formats that are industry standard like Iceberg, this allows us to pull in other engines. That basically, in addition to our built-in capabilities to run queries, even also accelerated queries for data skipping, you can use other engines in a very flexible way, like for instance Dremio, and we have a built-in we have published a Dremio connector to Dremio Hub that you can use to connect to this data lake very easily. But also out of the IBM portfolio, we have the big SQL engine. That's just another engine that you can use to connect and query this data here on Cloud Object Storage in the data lake. Now, the thing that we are rolling out, that's why I wanted to talk about this right now, because that's brand new. So you probably haven't heard about it yet. And actually, it's even not publicly available, but it's in closed beta. And that's why I'm talking about it. So if you are really keen to get very early hands-on, come to me, right? And we can organize a closed beta participation here. But it's not long out before basically this is available to everyone. And it's the stream landing. So what stream landing is basically pulling three services together. This SQL query service as a processing service to read and write data, the event streams data for message data transporting, and the Cloud Object store data for data at rest. That's all. We bring these three things together. And basically what we can do is you can basically turn topics into tables. Right? That's the value that you get out of that, right? I have a data on a topic here, but I would like to have it in a table. And with a few clicks, you can achieve exactly that. And then basically this data just starts to flow into this table and it's queryable. It's a fully managed thing that runs in the background. And it's basically based on the capacity unit that you pay per hour. And that's it. What you get with that is basically for your streaming data that is more or less ephemeral in Kafka, where you have to define, what's the basically time to live for this data, or what's the storage volume that you want to reserve before the data basically gets deleted. That's what Kafka is about. But now you get infinite storage. Right? You just throws in there and no data is lost. You can at any point go back and see analyze this data or review this data whatsoever, even play back this data. And run data warehouse analytics on top of that. Right? And this allows you to connect it to any kind of real-time data. It could be logging records, it could be clickstream data, IoT feeds, or even basically these change feeds from change data capture frameworks like Debezium. Okay, now I want to talk a little bit about solution patterns that you can, or that not just you can, that we see, right, where we know what we are working with customers and users. So I want to highlight this a little bit because these are things that we see others doing, and I want to share this with you. And I want to start with the real-time data lake solutions because that's really the hot thing that's why we're investing in it a lot right now, where we see a lot of demand right now. And I think the reason for that is why we see a lot of demand right now, because this is all data that is traditionally not persisted yet, that always basically was just there ephemerally, and where everybody knows there's a lot of value, gold basically in this data, and we need to get a hold on it, and in order to get the insights and the business value out of it, right? And these are things like audit trails, user behavior, right? So if somebody basically user journey through your product screens and basically why did he buy, why did he not buy, these kind of things. But we also see a lot of demand for basically IT related real-time data of your solutions that you have deployed in cloud. And especially if you build cloud native solutions yourself, this is the key to success. Data-driven decisions. How do you do data-driven decisions about your solutions? By collecting data, and not just by collecting it, by analyzing it. So these are things like network logs, and this is especially important for cloud-native solutions because they are very disaggregated, right? You have many different hops, many different microservices that you connect together. So the networking plays an important role, and you need to get a handle on that. But also the application logs themselves, what your application code is writing, or also cloud platform logs. And these are things like the services that you're using. What do they log, right? If you basically have a certain service that gives you certain error messages, maybe they basically have the stack trace that reveals something in the logs. So this is all of kind of IT-related important data. And they all basically go for the same infrastructure. Go into Kafka, go through our persistency layer into Cloud Object Storage, build up your data mart, your data model on Cloud Object Storage for this data, and then run analytics for that. We have, and at the top here, I've listed a little bit some basically types, incarnations of this. We see data log lakes. We started to call them log lakes. So basically data lakes for logs. We see data lakes for AI ops, right? They very basically want to do some machine learning on basically typical patterns and train models on your application behavior and find anomalies that you then can use later on to detect them in real time. You need a data lake to train these models, right? IoT data lakes, right? For all of your IoT, connected car, container, shipment, all this kind of stuff that continuously produces data. And compliance data lakes. That's actually an interesting one. You know what? You probably are all basically exposed to the requirements to do compliant solutions. Certain basically industry or also regulated industry standards that you have to satisfy, where you have to implement controls, where you have to prove certain things, right? That things happened that way or did not happen that way. And if basically a breach happens, I can find out who was it. How do you do that? It's all about basically IT data, logs, and these kind of things that you need to collect in order to compliance reports and analysts on top of that. It's nothing else than this basically that you then need to build out. And to make this easy, we are building integrations with different kind of consumption tools for analytics, like for instance, BI tools, Tableau, right? So we can, for instance, go here, and this is our documentation here of the service. We documented, you can set up Tableau. How do you set up Tableau to connect against this in order to build a BI report? Or we have integrations with Dremio, which is another very interactive query engine that is especially optimized for data lakes and also now has a lot of nice features to make it easily deployable in cloud, in Kubernetes, for instance. And that's also something where we have a built-in, or not a built-in, we have a published a connector to Dremio here. This is one of our repositories. And we have documented how you basically run it, also how you deploy Dremio in IBM Cloud, and things like that. It's all documented here. And Presto is just another engine that you obviously can also use. Grafana is another nice thing, especially for monitoring logging type data. That's a very popular interface. That's why we have developed and published also a plugin for that allows you to basically you build Grafana dashboards running these queries against this data lake here, all published here. And Jupyter Notebooks, right? I already mentioned that. That's for data scientists, where you can basically build out storytelling with notebooks interactively. It's also something where we have published in basically IBM Cloud. Actually, these other notebooks here, that's an example notebook that shows you how easy it is to basically do very natural Python notebook interactions with data on the data lake through SQL, basically. Okay, that's one type of solutions. Actually, this is the basic, I would say, the modern new type of solutions. But we also have a lot of customers that have existing big data systems, especially Hadoop systems. And they are asking for a way, what's the target solution stack for me and my users, right, to go to. And what we are doing now here is actually we are integrating that with Cloud Pak for Data as a service. Because Cloud Pak for Data provides a lot of tooling and other data analytic capabilities that can be put on top of this Cloud Data Lake to make it easy to use as an end-to-end data analytics stack for big data. So this is something that rides on top, using our services like Object Store, event streams, our Spark capability, the SQL Query service on top, but also other services of our Cloud Data platform, like our Cloud Database services. They all can basically be consumed and used from Cloud Pak for Data. And all of that together runs in IBM Cloud in a managed fashion. Right, so here's a little bit of the more end-to-end user journey idea that we are building out together with Cloud Pak for Data as a service. Right, it has different components and services inside Cloud Pak for Data, like catalogs and projects and connections to manage your data, to collaborate on data assets, and so on. This is playing a big role in the control, the data ingestion, management, data exploration, data governance, but then also basically to automate certain flows, right? For instance, using data stage, or there's also now a new Kubeflow pipeline service that's in the beta right now. That is really running Kubeflow, open technology, not just IBM proprietary data stage anymore. There's new ways to basically to automate workflows managed as a service. And finally, also our enterprise grade data science toolchain with Watson Studio, our data warehouse query engine with big SQL. So this is basically what Cloud Pak for Data enables. But the key thing is, also with that, it's wide open for various types of data ingestion, and it's wide open for various types of data consumptions and workloads that you want to connect at the end to it. That's an important takeaway that I want to make sure you understand here. It's just basically an integrated solution, integrated user experience that allows you to manage this whole stack end to end. That's what this Cloud Pak for Data as a service on top provides you. Now, I want to give you a brief outlook of what's coming, especially in the light of the topic of this conference here, right, the Cloud Native Day. Actually, IBM is investing heavily in serverless in general. And it's not a surprise that you see things like Code Engine, something that IBM is basically spearheading. And the way what we're doing here is really we're pulling this all together. We continuing really the strict conscious, basically, separation of state and compute so that we can scale independently. We are really doubling down all of our analytics processing going forward on IBM Cloud Code Engine, because that gives us this fundamental serverless fabric of serverless containers whenever needed, a lot of elasticity whenever needed, scaling to extreme cases up and basically down to zero when not needed. And yes, Spark, I already mentioned it. It's not something new. But we are actually, the thing that I want to point out is we are really actively engaging with other analytic frameworks that we are running on top, right? Not just Apache Spark. Apache Spark is just something that is very mature in terms of its capabilities, but also in terms of how we adopt it today already. So we are already further ahead to change the roadmap here. But there are other engines that we are looking at, like, for instance, Ray is something that we are evaluating here, and how we can connect it to this overall framework. And this is not just basically another engine. It's an engine that will be making use of the same kind of fabric underneath, right? Containers, but also the state, right? The meta store, the caching of data in memory, but also the way the data is streamed, the way the data is stored in cloud object storage. But we will make sure that those things will be reused, and basically a serverless compute ecosystem will be forming. So that's just to tease a little bit why we really think at IBM is really at the forefront of the innovation here in the serverless space. Okay, I have prepared a little bit more material that I was thinking of maybe going through if time allows. But before I do that, I have 10 minutes left. Let me check the questions, whether there's any questions I should pick up and make this a little bit more interactive here. Okay, I think I have some time to go over these additional material here. So one thing that allows us to really do a serverless big data framework like the one that I've just walked you through is, as I said, to separate storage and compute. What that, however, also means storage is remote, right? So storage is not something where we have a highly optimized local disk that is somehow distributed across all of the compute nodes whatsoever. No, it's really separate. What that means on the other side is that I/O is something that you need to be concerned about. I/O is something that needs to be optimized. And the way we do this is multifold. One is we consciously pick and support different data formats, and we also recommend certain data formats, right? So while any kind of structure will do it, a simple text-based file like a CSV is structure. It will do it, right? We can understand it, we can read it, we can infer the data types and all of that. We can go from there. But that's overhead. That's not a very efficient way to store the data, and it's in terms of volume, but also it has very little information about data types. So it's expensive to basically have a large data analytics on top of that. That's why we are basically recommending go for other formats that are more established and recommended for analytics like ORC and Parquet, because they also organize the data internally differently in so-called columnar formats. So that's not just a recommendation. We give you the tools to achieve that. So it's no problem to throw dirty, or let's say, not dirtier, but basically less smart formats like a CSV at us. You can ingest and restore these formats because it's just basically a simple serverless step away to turn these into Parquet, for instance. So we make it easy to basically come with your data, very little assumptions, and turn it into high quality data, also high quality in terms of optimization for analytics. That's the one dimension here, and things like Parquet and ORC, they have in itself also more structure and some metadata embedded that makes basically analytic engine like Spark much smarter in the way they can process this data, read it in parallel, and things like that. The other pillar that we're adding on top, and that's really an IBM invention that we also have open sourced now, is a data skipping indexing feature. And a data skipping indexing feature is really something where we are actively running scans on the data that you have stored. And we are deriving and producing out of that really indexed files that tell us, oh, for each file, let's say you have a terabyte or whatever, a petabyte of the table, right? Because it's thousands of objects that are stored on disk. And each one basically has a lot of data, a lot of millions of rows over many columns. We can index each individual file, and we know which file has basically for each column the minimum, the maximum value, the number of distinct value, but also things like if it's location data, we know we can understand location data like things like GPS tracks for IoT data, and we know, oh, this file only has GPS records in that bounding box on the globe. Right? So these are other types of special indexes that we can create that allow us, when a query comes in that filters for a certain region on the globe, we know we can skip all of those other objects because the bounding boxes will not overlap with what we are looking for. So that's what data skipping is. That's something that we've built, that we've integrated in our products, but also this fundamental library itself is something that we have open sourced very consciously, because we want to basically contribute back to the community what we are leveraging ourselves here: open technology, Kafka, Spark, Hive Metastore, all of these kind of things, Iceberg, Parquet. These are all open technologies. How it works, right? It's once we have indexed that, it's just an index file. What we have extended is the query compiler itself. When the query is compiled, there's an additional step basically that we are executing that knows when the query knows it has to scan to find candidates for certain rows in all of these objects. We can basically strike out a lot of those objects based on the metadata before we actually execute the query. So that's how this thing works. Right? And so, like for instance, here you get the idea. There's just 6 different files, Parquet files, but we know in each one there's a minimum maximum temperature for a certain measurement record, and we are looking for outliers now, right? We were looking for those weather situations where the temperature was more than 40 Celsius, and that's an outlier that basically not every file will have it because it's a rare condition, and that's exactly one of these things that we can use to very effectively skip I/O. Here's a different example for a location-based metadata index, right? Longitude, latitude values, where we can also look at minimum, maximum values and basically figure out these bounding boxes for these files and skip records. And all of that, we have done some benchmarking here. This is really some real data, 10 terabytes benchmark data, where we're running it actually, and we could get really factors of up to 10 to speed up the query execution just with that. One important thing I want to add, actually, minimizing I/O pays off twice in the cloud. Once, it gives you fast execution, like we just see it here. The other thing is because we have a consumption-based billing model, right? Your query actually has to scan less data, so we charge you less. So it really pays off twice. So it's really the big arc, basically, of leveraging cloud economics for big data is that. Okay. I also want to end basically with another reference that just basically give you a little bit of a proof point. That's something that we and my team have developed ourselves, basically an application of our platform for real data lake implementation. So IBM had engaged, it's about a year ago now, right, where IBM started to actively engage for the emergency response for the COVID pandemic. And we have engaged by building out a data lake for trusted data around Corona, around COVID-19. This was something that had to be done very quickly. This was something where we didn't have a big planning and big resources and so set aside. We had within really days, we had to come up with something. We couldn't go through all of the logistics to line up people, line up money for systems and whatsoever. No, we had to do something that can be very self-service with a few hand of developers with very minimal cost, develop, and we also didn't know what will be the long-run sponsorship of that. So we also had to develop something that where we know this could be run with very minimal operational and resource cost overhead. So we choose exactly our own platform for that because we know the qualities that it provides for that. Right? The serverless capabilities that give us the cloud economics. So we use basically these servers like object storage to persist all the data. We use cloud functions to automate all of those pipelines of collections. And for all of the data processing, heavy lifting, and querying, we use SQL Query. So that's what we've built out last year. With a data lake that looks like that. So that's just give you an idea. That's how basically this data lake is structured into different zones. And then we have different things built on top that are also publicly available, for instance, like Cognos dashboards, for instance, that can be publicly consumed on the IBM web pages. Okay, so this is what I've prepared for you for today, for the session. I want to say thank you very much for your attention. I hope this was valuable. And I'm happy. I will just go back to my title slide. If you have any further questions, ideas, projects, customers, just don't hesitate and come to us and come to me. I'm happy to chat with you. Thank you very much.